Hello, ladies and gentlemen. Welcome to the course Data Analysis 2. It's the second part of the data analysis course you have in this year. So let's take a look what we have done before. It was chapter 6 and we talked about advanced probabilities. Basically, we talked about the Bayesian ideas which we revisited from the first semester, and we say when speaking about bias, we also know that we consider the following three things that they interact with each other. So the prior distribution, the posterior distribution, and the likelihood. So then we could count over and over these things. So the prior probability, the posterior, and the likelihood, and also we got to know normalizing constant. Then the next what we have talked about, we added some more applications. So we have used the Titanic example throughout actually Python, and we added one more example that we haven't used in Python, that was medical studies. Then again, we talked about the random variables. A random variable uses real numerical values to describe a probabilistic event. And until now, we use fixed variables, so fixed value variables. Now we talked about random variables. Also, we talked about the discrete random variables. Say, a discrete random variable only takes an uncountable number of possible values, such as the outcome of a dice roll. You remember that x is 1, x is 2, x is 3, and x is 4, and x is 5 and 6, right? We also talked about the probability mass function that is about to describe the discrete random variable, right? And the character of the discrete random variable, and we talked about the variance. The variance of a random variable represents the spread of the variable, and it quantifies the variability of the expected value. After that, we also talked about Likert chart, and then we moved to types of random variables. Binomial, right? So binomial setting has the following four conditions. The possible outcomes are either success or failure. The outcomes of trials cannot affect the outcome of another trial, and the number of trials was previously fixed, so it's a set. And then the chance of success of each trial must be always equal to P. Let's also look at the next one. So the next one is, and then we went through some examples, and the next one is geometric random variables, the second discrete random variable. It is actually quite similar to binomial random variable, and that we are concerned with the setting in which a single event is occurring over and over. Now the difference is that we are not fixing the sample size. So in the geometric random variables, we do not fix the sample size. So the possible outcomes are either success or failure. The number of trials is not set. The outcomes of trial cannot affect the outcome of any other trial, and the chance of success or failure must always be P. Right now, this is also done. For that, we have seen an example, and the third and last specific example of a discrete random variable is a Poisson random variable. To understand why we would need this random variable, imagine that an event that we wish to model has a small probability of happening, and that we wish to count the number of times that the event occurs in a certain period of time, or in a certain time frame. So consider the following examples for Poisson. So finding probability of having a certain number of visitors on your site within an hour, knowing the past performance of the site, and estimating the number of calls or car crashes actually at an intersection based on previous police reports. We then talked about continuous random variables, so not countable but infinite number of possible values, and we called the functions that describe the distribution density curves instead of PMF. We use here the probability density function. The PDF is the continuous random variable version of the PMF for discrete random variables. Here we use also the standard normal distribution and the standard deviation. So the mean is mu, the standard deviation is sigma, and we looked at some programming samples as well. And now this time we can continue finally with basic statistics. So this chapter will focus on the statistical knowledge required by any inspiring data scientist. We will explore ways of sampling, obtaining data without being affected by bias, and then use the measures of statistics to quantify and visualize our data using the z-score or z-score and the empirical rule. We will see how we can standardize data for the purpose of both graphing and interoperability. And then we will do the following again: how to obtain and sample data, then measure of center of variation and relative standing to each other, and then normalizing or normalization of the data using the z-score or z-score, and then the empirical rule, and we actually finish thereafter. So then let me continue. Okay, now what are actually statistics or basic statistics? Let's see some related theory. Okay, so well, this might seem like an odd question at all, right? But actually, the author says that he receives frequently this kind of questions. So, what are actually statistics? Statistics are the numbers you always see on the news in newspapers. Statistics are useful when trying to prove a point or trying to scare someone. What are they actually? Well, to answer this question, let's get back up for a minute and talk about why we even measure something in first place. The goal of this kind of field, so statistics, is to try to explain and model the world around us. To do that, we have to take a look at the population. We can define a population as the entire pool of subjects of an experiment or a model. Now, essentially, your population is who you care about. Who are you trying to talk about? If you are trying to test whether smoking leads to heart disease, your population would be the smokers' world, right? Because non-smokers, you cannot check here. If you are trying to study teenage drinking problems, your population would be all the teenagers, not grandmas and grandpas. Now consider that you want to ask a question about your population. For example, if your population is all of your employees, assume that you have like 1,000 employees, perhaps you want to know what percentage of them use illicit drugs. So the question is called the parameter. We can define a parameter as a numerical measurement describing a characteristic of a population. For example, if you all ask, right, all the 1,000 employees and 100 of them are using drugs, the rate of the drug users is like 10%. The parameter is here 10. Now, however, let's get real. You probably can't ask every single employee whether they are using drugs or not. What if you have then like 10,000 employees in a company? Can you still ask them, each of them? You don't. You can't. It would be very difficult to track everyone down in order to get your answer. When this happens, it's impossible to figure out this parameter. In this case, we estimate the parameter. First, we will take a sample of the population. Yes, we can define a sample of population as a subset of that population, so a part of that population. Now, as next, so let's see here as a sample. So we perhaps ask 200 of the 1,000 employees you have, and of these 200, suppose 26 use drugs, making the drug use rate 13%. And yes, here then 13% is about the parameter. It's the parameter itself, because we don't get a chance to ask everyone. We can only estimate. So this 13% is an estimate of the parameter, actually. My bad. Once again, the 13% is just the estimate of the parameter. So now, if this is an estimate, then you already know what we call statistic. This is the statistic. It's an estimate of a parameter. It's these kind of numbers we can only estimate because the population itself we cannot check, we cannot control over the time. So we can define a statistic as numerical measurement describing the characteristics of a sample of a population. Statistic is just an estimation of a parameter, just as I mentioned. It's a number that attempts to describe an entire population by describing a subset of that population. This is necessary because you can never hope to give a survey to every single teenager or to every single smoker in the world. That's what the field of statistics is all about, taking samples of populations and running tests on these samples. So the next time you are given a statistic, you remember that the number only represents a sample of that population, not the entire pool of the subjects. So, but how do we obtain and sample data? If statistics is about taking samples of populations, it must be very important to know how we can obtain these samples. And well, yes, we really have to do that. Let's focus on just a few of the many ways of obtaining and sampling data. So there are two main ways of collecting data for the analysis: observational and experimental. Both ways have their pros and cons, of course. Yeah, they each produce different types of behavior, and they are used for different types of analysis. Let's talk about observational sampling. Now, obtaining data, so if we might obtain data through observational means, which consists of measuring specific characteristics, but not attempting to modify the subject being studied. So for example, if you have a tracking software on your website that observes users' behavior on that website, such as a length of time spent on certain pages, what was looked at, right, the clicking rate on ads, all the while not affecting the user's experience, then that would be an observational study. This is actually, of course, obviously, is one of the most common ways, because it's really easy. All you have to do is just observe and collect data. Observational studies are, that's why, also limited in the types of data you may collect. This is because the observer is not in control of the environment. You may only watch and collect natural behavior. If you are looking to introduce a certain type of behavior, observational study wouldn't fit, but the experimental one. An experiment consists of a treatment and the observation of its effect on the subject. Subjects in the experiment are called experimental units. This is usually how most scientific labs collect data. They will put people into two more groups, so usually just two, and we can call them the control and the experimental group. The control group is exposed to a certain environment and then observed. Then the experimental group is also exposed to a different environment and then observed. The experimenter then aggregates data from both of the groups and makes a decision about which environment was more favorable. Favorable is a quality that experimenter gets to decide. So, in a marketing example, consider that we expose half our users to certain landing page with certain images and a certain style, so website A, and we measure whether or not they sign up for the service, and then we expose the other half of the group to a different landing page, different images, and different styles, that is the website B, and again measure whether or not they sign up. We can then decide which of the two sites perform better and should be used going further. This is called the A/B test. Here we go. This is called the A/B test, and we can see an example in Python as well. For this, let's suppose we run a preceding task and obtain the following results as a list of lists. This example is actually just a sample, so we can't really do it because we don't have the exact data. Anyway, so if we get back here, then we see here. So each object in the list result represents a subject person, and each person then has the following two attributes: which website they were exposed to, represented by a single character, and whether or not they converted. So 0 for no and 1 for yes. We can then aggregate and come up with the following result. You see here, user exposed to A, user exposed to B. So we get a list each time. And once we create these two lists that will eventually hold each individual conversion, Boolean 0 or 1, we will iterate all of our results of the test and then add them to the appropriate list as shown. So for website, converted in results, iterate through the results. Okay, so we will look as something like a website equal A and converted 0 if website A, and my bad that the structure is incorrect at this time. So let me correct the structure. There you go. So once again, user exposed to A, append and converted, and L if website B, user exposed to B and append converted only, right? Now each list contains a series of zeros and ones. We know that. So remember that 1 represents the usual actually converting to a site after seeing the website or the web page, and the 0 represents that the user seeing the page and leaving before signing up or converting, so clicking basically. To get the total number of people exposed to website A, we can use the length, so the len function feature in Python as illustrated. So len user exposed to A, then we get a number, and user exposed to B, then we get another number. To count the number of people who converted, we can sum up. So here we see that the entire sum is 54, and we have another sum for website B, which is 48. Yet again, as this is just a small example, it's not a complete programming here. So if we subtract the length of the list and the sum of the list, then we are left with the number of people who did not convert for each. So here we have 134 didn't sign up or did not convert, and 54 did, and here 110 did not, and 48 did. This is what we get in the table. So we can aggregate and summarize our results in this table. Now this represents our experiment of website conversion testing, and we can quickly see some descriptive statistics. We can say that the website conversion rate of the two websites are the following. So conversion rate for website A is 0.288, so 28.8%, and the conversion rate of the for the website B is 30%. Well, there is not much difference, but a little bit. And even though B has the higher conversion rate, can we really say that version B significantly converts better? And not yet. To test the statistical significance, of such a result, a hypothesis test should be used. This test will be covered very soon. Now, okay, let's see if you can squeeze in anything else into this video right now, or we have to close it. Let's see it. So yes, indeed, we can continue with sampling data, and we have here probability sampling, random sampling, and unequal probability sampling. Okay, so probability sampling is the first. About sampling data, well, remember how statistics are the result of measuring a sample of population? Well, we should talk about two very common ways to decide who gets the honor of being in the sample that we measure. We will discuss the main type of sampling called random sampling, and which is the most common way to decide our sample sizes and our sample members. Now, probability sampling is a way of sampling from a population in which every person has a known probability of being chosen, but the number might be a different probability than another user. The simplest and probably the most common probability sampling method is a random sampling. So, random sampling, suppose we actually run an A/B test, and we need to figure out who should be inside the group A and who should belong to group B. Therefore, there are three suggestions, well, from your data team, or from your team, or from yourself. Well, separate the users based on location. In the States, we can do this easily because we have the West Coast and an East Coast, and it says put the West Coast people into Group A and East Coast people into Group B. Separate the users based on the time of day they visit the website. So again, users who visit between 7 p.m. and 4 a.m. are in Group A, and the others are in Group B. And then again, make it randomly so-called completely random. So that means every new user has a 50% chance of being placed in either group. Wow, you see that the first two are valid options for choosing samples and are fairly simple to implement, but, and here it comes, both have one fundamental flaw. They are both at risk of introducing a sampling bias. Now, a sampling bias occurs when the way of sampling is obtained systematically favors another outcome over the target outcome. So again, here, systematically favors another outcome over the target outcome. It is not difficult to see why would it be like that. So option 1 or option 2 might introduce bias. If you choose or if you chose groups based on where they live and what time they log in, we are priming our experiment incorrectly, and now we have much less control over the results. Specifically, we are at risk of introducing a so-called confounding factor into our analysis, which is really not a good news. A confounding factor is actually a variable that we are not directly measuring, but connects the variables that we are being measured. So a confounding factor is like the missing element in our analysis that is invisible but affects our results. In this case, option 1 is not taking into account the potential confounding factor of geographical taste. And for example, if website A is unappealing in general to West Coast users, it will affect your result drastically. Similarly, option 2, introduce a temporal time-based confounding factor. What if website B is better viewed at night-time environment which was reserved for A, and users are reacting negatively to the style purely because of what time it is? These are both factors that we want to avoid, so we should go with option 3, which is complete random sampling. Now, while sampling bias can cause confounding, it is different concept than confounding. Option 1 and 2 were both sample biases because we chose a sample incorrectly, and were also examples of confounding factors because there was a third variable in each case that affected our decision. A third variable which we don't know yet, right? So a random sample is chosen such that every single member of a population has an equal chance of being chosen as any other member. This is probably one of the easiest and most convenient ways to decide who will be part of your sample. Everyone has the exact same chance of being in any particular group. Random sampling is an effective way of reducing the impact of confounding factors. Now, let's talk about unequal probability sampling. Recall that we previously talked about it, that the probability sampling might have different probabilities for different potential sample members. But what if this actually introduces problems? Suppose we are interested in measuring the happiness level of our employees. We already know that we can't ask every single employee, every single member of the staff, because that would be very exhausting and costly, so expensive. So we need to take a sample. Our data team suggests random sampling, and at first everyone high fives, yay, because they feel very smart and statistical. But then here comes a very harmless and clever question. Does anybody know the percentage of men against women who work here? Silence just come in. This question is extremely important because sex or gender is likely to be a confounding factor. The team looks into to discover a split, and they see 75% men and 25% women in the company. This means that if we introduce a random sample, our sample will likely have a similar split and thus favor the results for men and not women. To combat this, we can favor including more women than men in our survey in order to make the split of our sample less favored for men. Well, but at first glance, okay, let's go back. Introducing a favoring system in our random sampling seems like a bad idea. However, elevating unequal sampling and therefore working to remove systematic bias among gender, race, disability, and so on is much more pertinent. A simple random sample where everyone has the same chances as everyone else is very likely to drown out the voices and opinions of minority population members. Therefore, it can be actually alright to introduce such a favoring system in your sampling techniques. So, how do we measure statistics? We continue from here. This is the next topic within the next video. Let's look at it, what we have just done very quickly. So we started with the statistics, explaining what is population, what is parameter, what is an estimate of parameter, and a sample as well. We realized what statistics is, and then we moved forward how to obtain, obtaining data observational and experimental ways. Observation just to observe, and it have no impact on the sample at all. And experimental is exposing one group and the other, and then comparing them how they react on different things. This is what we had. Then we had a Python example, which we can't actually use very well because the data is not included. But however, we can still see the conversion rate for website A and website B. And now here you see as well, to test the statistical significance of such a result, hypothesis test should be made. And hypothesis test actually we can learn in chapter 8, if I remember well. So we then learned about sampling data, so probability sampling, and the simplest method of probability sampling is random sampling, and we see here some random sampling way, and we learned about the sampling bias, the confounding factor, which leads to a third variable or unknown variable, and then unequal probability sampling talks about the favoring of one or the other. That's it. Let's close this topic for now, and we can continue with how do we measure statistics the next time. Thank you very much for your attention, and here I close it, and see you the next time. Thank you. Bye for now.